Okay, so good morning, everybody, and welcome to the start of this third course for the series intended for this school. So, the title of the course is Exactness Matrices and Applications. So it's a concise title, so I can start probably by explaining it slightly better. So S matrices, you know here that S stays for scattering, and that the S matrix is essentially a chapter of quantum field theory devoted to the description of the theory in terms of particles. So we will be dealing with field theory, which, as you know, is a very successful tool of theoretical physics with applications which range from statistical mechanics to condensed matter to particle physics. And you know, also is somehow a quite non-trivial tool at the same time. So it's quite sophisticated to the point that in the particularly interesting cases where there are interactions in the game, the best you can do normally is perturbation theory. So it becomes soon in general the realm of Feynman diagrams and expansions and so on. So a main feature, essential feature of what we are going to do here is to deal with field theory in a non-perturbative, exact way. And this is something that, for reasons that we are going to see, is possible in 2 dimensions. So what we are going to deal with is 2-dimensional field theory. So when we are in 2-dimensional field theory, there are, roughly speaking, 2 main directions we can take, moving towards applications. So the first one, so it depends on how we use these 2 dimensions we have. The first one is to consider classical equilibrium. Statistical physics in 2 space dimensions. And the other way is instead to consider the 2 dimensions as 1 space dimension and 1 time dimensions. So here we move towards quantum physics in 1 + 1 dimension. Now, as we will see, the formalism behind is very much the same, and to the point that we will jump freely at a certain point very soon from one language to the other. But as far as the applications I will discuss in these lectures are concerned, I will focus towards this block here. So, and some main keywords, or what I will be discussing on this side, will be things like magnetism, percolation, phase separation, interfaces, wetting, okay, so these are some main keywords that are going to appear. And there are two essential features that we will pursue all along these lectures. So the first one is that we will be dealing uniquely with universal properties. Where this word universal will be explained in a moment. And as I said, the other essential point is that we will do exact descriptions. So exact results. So this introductory lecture of today is devoted to actually to explain most of the words I've been using here, and so to establish a vocabulary and notations that then we'll use in the rest of the course. So most of the things I will say you know already them, but it is necessary to fix some starting points. Okay. So let's start from classical equilibrium. Stat mech. Now, for reasons that will become clear in a moment, the simplest and most convenient thing is to think of systems discretized on a lattice. So we will be in two dimensions. I will normally draw the square lattice, but it could be any regular lattice, triangular, hexagonal. Okay. So at each side of such a lattice, there is a site variable, sigma i. So this sigma I is it is called normally the spin variable. At site I. So there is one for each site, taking a set of values depending on the model. Then the model is characterized, the system is characterized by an Hamiltonian, H, which is a functional of the configuration of the system. So it specifies the energy of the configuration. Then with this, we can take statistical averages of a generic observable O in the usual form, 1 over Z, sum over all configurations, the observable, and then the weight exponential minus the Hamiltonian, the energy over T, where T is the temperature. And Z, of course, is the partition function, which is sum over configurations of the weights. So it's a normalizing factor, ensuring that the average of the identity is 1. Okay, so in this context, we are interested in systems which, in the thermodynamic limit, namely when this lattice becomes infinite in all directions, exhibit phase transitions. Which are normally associated to the spontaneous breaking of some symmetry. So I call G the group which, acting on the Hamiltonian, leaves it invariant, and so provides a symmetry for the system. So what happens here is that when the temperature goes to 0, the system wants to stay into a configuration of minimum energy. We call ground states such configurations of minimum energy. Now, in presence of a symmetry, normally there are several of such ground states. So at some point, the system chooses one of these. And this is called the spontaneous breaking of the symmetry. And what happens is that the order parameter which is the average of this spin or order variable, will be 0 for T larger than some critical temperature, Tc, which is the transition temperature, and non-zero below. Then we will distinguish further two situations. If we go to Tc from below and look at the order parameter, this can be 0, so this means that, different from 0. This means that the order parameter is discontinuous at Tc. And so we say that this is a first order transition. If instead this is 0, we have a second order, or more generally continuous transition. Okay, with these basic definitions, now we can move towards specific models. We will enumerate a few of them, because we will play with them in the rest of the course. And as you know, of course, the basic model exhibiting such a phase transition is the Ising model, with Hamiltonian where this sigma I, the side variable, takes two values, plus or minus 1. And of course, as you see, the symmetry group here is the simplest one. This So the Hamiltonian is invariant under reversal of the sign of all spins. This notation here indicates that the sum is performed over nearest neighbors, spins, so it's the simplest thing you can do. I will refer to the ferromagnetic case in which J is positive. So at low temperature, the spins want to be aligned. So there is, in this model, there is a continuous transition at Tc, and what happens is that if you plot the order parameter as a function of temperature, there is Tc, so something like this, and so this is 0. More precisely, here there is some singular behavior, as you see, and this is characterized in the following way. The order parameter behaves as b to Tc minus t to an exponent beta when t goes to Tc from below. Now, this beta is the first example of a critical exponent, while the amplitude here is called just critical amplitude. So this is a one-point function. We can look at two-point correlations. Okay, so, this, let me just say that this decays as exponentially with the distance between the spins normally. So as and this exponential decay defines this length here, psi, which is the correlation length. Now, an important feature here of continuous transitions is that the correlation length diverges at criticality in the following way. You have some critical amplitude psi 0 and some critical exponent nu. This as t goes to Tc. So the critical amplitude depends actually if you approach criticality from above or from below, but the exponent, the critical exponent doesn't. Another quantity that we will have in mind is the susceptibility. I will denote it by chi. This is 1 over n. This n is the number of sites, which goes to infinity into the thermodynamic limit, and then sum over j sigma I, sigma j. So this is the definition of susceptibility. This behaves at criticality as second order transitions, again some amplitude, and t minus Tc to an exponent that now is called gamma. Now, what is observed is that these critical exponents are introduced up to now, so this beta, nu, gamma, are universal. In the sense that they do not depend on the microscopic details of the system. By microscopic details, I mean the fact that we are on the square lattice rather than triangular or hexagonal. So they do not depend on the specific lattice. They do not depend on the fact that here we took nearest neighbors. We could add next to nearest neighbors interaction, and still you will observe the same exponents. So this is, so in the end, this means that they depend only, essentially, they are characterized by the symmetry G in a given dimensionality. Okay, so if you change the dimension from d equal 2 to d equal 3, keeping the same symmetry, these numbers will change, but for a fixed dimensionality, essentially they depend only on the symmetry. Concerning the critical amplitudes, they are not universal themselves, but they can, out of them you can construct some universal quantities, which are these, for example, these ratios. You take ratios of amplitudes, in which, taking the ratios, you see, you cancel the so-called metric factors. This amplitude multiplies some the difference from critical temperature. This will be measured in some units, so the amplitudes know about these units in general. But if you take the ratio, the dependence on the units drops out, and these are also universal. So the system, the collection of the systems which share these properties, so identified by numbers, universal properties like this, are said to form a universality class, which is characterized by the symmetry. Okay, so now that we have introduced these main definitions, we can move on more rapidly and look at other universality classes. So a basic generalization of the easy model is the Q-state Potts model. This is the as the Hamiltonian minus j sum over nearest neighbors of delta Si comma Sj. Well, this Si takes Q values, is a site variable taking Q values, 1 to up to Q. So in the Hamiltonian you have a Kronecker delta, which just checks whether two nearest neighbors have the same value or not. So the symmetry of this Hamiltonian is the permutational symmetry of these Q values, SQ. Okay, you see the actual values are not really important. The important thing is if nearest neighbors have the same or different value. So I will often refer to this as Q different colors. So for the ferromagnetic model, in this case, a lot of this will have Q different ground states. Each one, in each ground state, all the spins have the same color. Let me define also this variable. So the order, the proper order variable here can be defined this way: delta Si comma alpha minus 1 over Q. So we have at site I a component for each color, and when the symmetry is unbroken, the probability of finding a color is 1 over Q. So with this subtraction, this is 0 above Tc. Of course, for Q equal 2, you recover the easy model. Now, a very interesting feature of the Potts model, the Q-state Potts model, is that it allows for a graph expansion. in which the partition function, which in the spin language is written as we know, this can be shown. You can check this as an exercise, that this can be written exactly up to a constant which is inessential as a sum over graphs of with a weight p to the nb 1 minus p to the nb bar and q to the nc, where so p is related to the original coupling as a minus j over t. Then G is a graph on the lattice made of bonds that we put on the edges. So we will have the lattice. So a graph will be a collection. You put bonds in all possible ways. So each configuration of bonds will be a graph, and you sum over all of them. Then NB is the number of bonds in G. NB bar is the number of absent bonds. And NC is the number of clusters. So I call clusters the connected components in the graph. So here you would have 1, 2, 3. But there is a subtlety here, because in this mapping, you have to count as a cluster also the sites which are not touched by any bond. So these, all these sites also have to be counted as clusters. Okay? So why this is interesting? Well, first of all, you see that now in this graph expansion, Q appears in this form and can be taken as a continuous parameter. So this graph expansion makes sense of the Potts model for Q continuous. So no longer an integer. And the second point is that now, since Q can be taken continuously, you can take in particular the limit Q going to 1, in which the weight now of the configuration is P. So this in the limit, this factor drops. You are left with P to the number of bonds, 1 minus P to the number of missing bonds. And this is the weight, actually, that you have in the percolation problem. So percolation is a purely random problem in which you put bonds on a lattice. You consider all possible configurations. And the phenomenon is interesting. You weight them, each configuration in this way. So P is the probability that a bond is present. And 1 minus P is the probability that the bond is absent. So the reason why this is interesting is that there exists a critical occupation probability, PC, in percolation, such that for P larger than PC, an infinite cluster is found with a non-zero probability. So for P larger than Pc, you have an infinite cluster, said shortly. So you see this is a critical phenomenon, but somehow of a different type or the ones I've discussed before. So this is often referred to as the prototype of geometric phase transition. There is no Hamiltonian. But what we are seeing is that through this mapping, the geometric phase transition in percolation can actually be seen as a limit for Q going to 1 of the thermodynamic phase transition of the Q-state Potts model. So this is why we get an handle on percolation. Okay, so last model I want to introduce for the time being. Is also very well known. So is the ON vector model. So here the Hamiltonian is, as usual, minus j sum I j sigma I si scalar sj. Well, these si now, the side variables, are n-component vectors of length 1. So n-component unit vectors. And you see from the form of the Hamiltonian that the symmetry is the group On of rotations of these vectors. Now, for n equal 1, you are back to Ising. For n equal 2, the model is most often referred to as the XY model. So this is just names that this is useful to know. Now, it is interesting that also the vector model allows for a graph expansion. I will not detail this expansion, I mean, in a very precise form, because actually you have to start from a slightly different Hamiltonian, which anyway is in the same universality class. So this is what matters for us. But the main point is that n in this expansion, n appears in the weight in the form n to the number of loops, because the expansion is an expansion. Now the graphs you expand on are loops things like this, okay? So you get this n dependence. So once again, it's like the Q-state Potts model. Since n appears like this, it can be taken continuous again. And in the limit, in particular, you can take the limit n going to 0. sum over loops. Yeah. So the graphs here are graphs made of loops. And so in the limit n going to 0, you see the sum, the partition sum, is dominated by the configuration with a small number of loops. In particular, the first non-trivial configurations are those with one loop. So in this limit, what you recover is the problem of the self-avoiding polymer or self-avoiding walk. So you have one loop which takes all possible configurations on the lattice, and you are studying the statistics of such an object, self-avoiding. Now, actually, this self-avoiding property is something which doesn't really appear from what I've said. And actually, on the lattice is slightly subtle. You have to do it some careful study. But it is a property of the universality class, and we will see this directly in the continuum later on. So for the time being, I just mentioned that it is there. Okay. Are there questions up to this point? Oh, sorry, I just erased.
It's okay. You have that sigma I alpha is delta Si alpha minus 1 over q.
Yeah.
Why do we have minus 1 over q?
Okay, let me repeat this. Well, it's not needed to write it. When you take, I defined the order parameter as an object which above Tc is 0. Now, if you take the average of that sigma I alpha, so the average of the delta above Tc is 1 over q, because you see each spin has probability 1 over q to appear, because the symmetry is unbroken. Okay? Other questions? Okay, so we have universality classes, and we want to study them. We have seen that universality occurs in correspondence of second-order transitions, which are characterized by the divergence of the correlation length, nearby criticality. And actually, as you understand, this divergence of psi is actually the main point behind this universal behavior. Because what's happening behind this is that when you approach Tc, so you have correlations over very long distances, so much larger than lattice spacing. And what really contributes to these universal properties and allowed them to emerge is the physics which happens at these large distances. So this is said in few words. So since this is why these microscopic details become negligible, and this is why it is natural to think that all these universal properties will be most naturally captured within a continuous description. So, and this continuous description is actually field theory. Okay, let me put this way. Okay, yeah. So now, in few words, I will sketch the dictionary between the lattice and the continuum, field theoretical description. So we have, say, on one side, the lattice that we described up to now, and then we want to go to a continuum approach. And the dictionary will be like this. So to a site I on the lattice will correspond a point x in the continuum. And the continuum for us, we are in 2 dimensions. So will be a point with coordinate x1, x2 in 2-dimensional Euclidean plane. Then we replace the site variable, sigma I, so quite naturally by a continuous variable, which now depends on sigma, on x. And this is what we call a field. So in particular, this one, it will be the order or spin field. Then another field which plays an essential role is this. So locally, in the lattice Hamiltonian, you have an object that we can write like this: sum over j, nearest neighbor of site I. And then typically you have something like sigma I, sigma j. So this, in the continuum limit, will be, so this depends on site I. So the continuum will become a field that we denote by epsilon of x and call, quite naturally, energy density field. Next, so a crucial ingredient which defines the lattice system is the Hamiltonian. Let me also rescale by the temperature. So in the continuum, we will have some continuum version of this. And I will denote this by A and call it, for reasons, I mean, it's quite usual to call this Euclidean action. Is a name. You may know that the origin of this name, but if you don't, it doesn't matter. Then, of course, the partition function becomes, in the continuum, the sum over, now we have to sum over field configurations. Sum over field configuration. This is quite formal, you see, but we don't need to, for our purposes, to make this more precise, of exponential minus the action. So this is the natural translation. Okay, now to continue, we start from the critical case. So we start first of all from TC. So at TC, we are dealing with second order transitions. So psi correlation length is infinite. Now the correlation length provides in your system the typical scale. If it is infinite, this means that you are left with no scale in the system. So this is why, in few words, these critical systems, second order transition points in the continuum limit, are characterized by scale invariance. So in particular, this means that in the Hamiltonian you have no dimension-full coupling. Because if you have some dimensions-full coupling, this introduces a scale, which breaks the scale invariance. Okay, then another consequence of scale invariance and divergence correlation length is that if we consider I will denote a generic field by phi. Okay. If we consider a two-point function of a field phi, in a scale invariant situation, I mean the exponential decay, which holds in general, in generic cases, since psi now is infinite, is replaced by an algebraic decay. So it is a consequence of the divergence of correlation length. And this is, so in general, we write this as a constant divided the distance times an exponent, which I call twice x phi. This is a capital X. Sorry, please do not confuse with the coordinate. So let me say once for all that when I write this, so I'm saying that implicitly that the correlation depends on the distance. This is true for fields which are rotational invariant. So I call these rotational invariant fields scalar fields. For short. So it's a piece of jargon that I ask you to keep in mind. Then the other important thing here is this quantity x phi, which is called the scaling dimension of the field phi. So you see the logic here. I put this factor 2 because each field carries a dimension x phi. So the idea is that x phi is the dimension in units of inverse length, as you read from here. And in the units I will use throughout, an inverse length is like a mass. So this is inverse length dimension or mass dimension. And all the objects we will write at a critical point will carry a dimension of this type. Okay, with this we can now move away from TC. Away means for us not TC but somehow nearby, in such a way that psi is no longer infinite, but somehow still is very large compared to lattice spacing, in such a way that our scaling reasonings apply. So T close to TC. So how do we characterize this? So the statement is the following. We characterize the system close to criticality by an action, which we construct this way. We start with the action of the critical point, which I call the scale invariant action. So this is the action of the scale invariant point t equal tc. And then we have to move away, slightly away from this point, which is something that we do adding. You remember that we introduced the energy density, epsilon of x. So we add this term, which moves us away from Tc, where this T is precisely measuring the deviation. This tau is measuring the deviation from Tc. Now you remember that actually we had written that psi diverges as t minus tc to the power minus nu. So now we can invert this relation. So up to a constant, this will be psi. Well, let me put, sorry, different way. So it is more important here to stress another point. Tau appears in the action. The action is dimensionless by construction. So since the field epsilon has a dimension, scaling dimension x epsilon, also tau will have a dimension such that the total object is dimensionless. And this dimension is a length, the correlation length, to the power minus 2 minus x epsilon. Okay? If you put this tau with this dimension here, the action is dimensionless, because you cancel the dimension of the field, you cancel the dimension of the integration measure, and what is left is dimensionless. So this is the dimension of tau. And if we remember how we had written that psi depends on Tc in terms of an exponent mu, from here we read that mu is actually 1 over 2 minus x epsilon. So what we start seeing here, this is the first example, from which we see that the critical exponents actually are determined by the scaling dimensions of the fields, which are the truly fundamental quantities to characterize scaling behavior. So similarly, we can now you can play this game with other quantities like the order parameter. So dimensional, this will be psi to the minus x sigma, scaling dimension of the spin field. But again, now we can use this relation to go to dependence from T minus to Tc, and recalling the definition of the exponent beta, you can check immediately that this is x sigma over 2 minus x epsilon. Similarly, susceptibility. In the continuum, this is the integral over all sides of the two-point function of the spin. Dimensionally, this is length, correlation length, to the minus 2 from the integration measure, and then we have twice the dimension of the spin. And from this, again, going to T minus Tc, you find that gamma, which was the critical exponent of the susceptibility, is 2 minus 2x sigma over 2 minus x epsilon. Okay, so this is enough to show what I just said. The problem of critical exponents is reduced to the problem of determination of the scaling dimension of the spin field and energy density. So from now on, somehow we will forget about alpha, beta, gamma, nu, and we will only look for scaling dimensions. X sigma, x epsilon. Now, one thing that you see also is that these scaling dimensions are defined at criticality. So they, in the end, they will be determined by the theory, the field theory, which describes the critical point. So these are quantities that also theoretically, not only experimentally, can be determined at criticality. It is different if we go instead to the other universal quantities we had introduced, which are were the ratios of critical amplitudes. So, for example, we had introduced gamma plus over gamma minus. Now we understand that now this for us will be the ratio of the susceptibility computed in the field theory with above Tc, so tau positive, divided by the same object computed in this theory always with tau negative. And of course, you see from here, so in this ratio, all the dimensions drop, and you're left with some universal number. And of course, you see that to compute these kind of things, you need to compute the correlation functions in this theory, away from criticality. By the way, let me give a name to this action. So this is the action which is called scaling normally. It's called the scaling action, and determines in the way I've just illustrated with examples the universal properties of the system. So actually, it's the action which describes the universality class associated to a given symmetry. The symmetry will be hidden here, so this scaling invariant part will be invariant under the symmetry, and also the field, the energy density will be invariant. Okay, so this is a good point to take the break. And if you have questions before that. That's good. Okay, so we saw universality, and we saw in a very essential way how we characterize universality in the continuum limit in field theory. But now the last step I want to take in this introduction is to introduce the particle description, which is in my title. So my title is scattering matrices, and the scattering, the objects which scatter are the particles. So where are these particles? So the systems we consider, first of all, are such that all the systems I will discuss are such that when I take the continuum limit, they are isotropic. Of course, on the lattice there is some discrete nature, but when you take the continuum limit, they become isotropic, which means that they are invariant under rotations. So the action, the scaling action, is invariant in particular under rotations in the Euclidean plane. This is why epsilon, the energy density, is a scalar field in the way I defined it. And this is why the field theories I introduced are called Euclidean field theories. So we are in Euclidean field theory in two space dimensions, as we have seen. So these two dimensions are the coordinates x1, x2 in the Euclidean plane. Now, what we can do, and what we will do regularly, you see, starting from such an Euclidean field theory, you can do kind of analytic continuation in which you interpret this second coordinate, x2, as it, where t is a time coordinate, in such a way that this x2 becomes what we call the imaginary time in this correspondence. But now, through this continuation, so we will have one space dimension, x1, and one time dimension, t. So we are switching from this Euclidean field theory into, on the plane, to a quantum field theory. In one space plus one time dimension. And I repeat this, one space dimension is x1 and one time dimension is t. Now, in this Euclidean field theory, the quantity which is invariant is the distance from of a point, say, Euclidean distance of a point from the origin. This is invariant under rotations, Euclidean rotations. On this side, to this correspondence, the quantity which is invariant is this, which is the distance of an event from the origin of events. And the transformation which leaves this invariant is called a relativistic transformation. So, Euclidean rotation invariance under this analytic continuation brings us to a relativistic invariant theory in one space and one time dimension, said in very few words. Now, the two theories, essentially, they have the same field content, so the same scaling dimensions. So they are very much the same thing. The only difference is that when we compute correlation functions, to switch from one to the other, we have to perform this continuation from real to imaginary time. So this is something we will do quite regularly from now on. But why I'm doing this continuation? Well, the reason is that, as you know, a quantum field theory incorporates somehow, in a very natural way, a description in terms of particles. And the particles I will be dealing with, since the theory is characterized by relativistic invariance, will be relativistic particles. So we will have relativistic particles in the real-time picture. Relativistic particles means that the energy and momentum are related by this dispersion relation. Epsilon squared is p squared plus m squared. So E is the energy, P is the momentum of a particle, and m is its mass. Now, in a quantum field theory, the way you deal with these particles is by describing the way they scatter, they interact among them. And the more general scattering process, so if we now go in our real-time framework, where here there is x1, this is time, so time runs upwards for us. What we have is that, so we have in the initial state a collection of particles. Let me draw this. With momenta, say, P1, P2, up to Pn. So we have in the initial state some n particles with their momenta, and their energies specified by this relation. And then they, so at time t minus infinity, they are very far apart from each other, and then at some point they approach to each other and they interact, they scatter, as one says. So something happens, there is some scattering event, and after this scattering event, I will have some final states, final state, which the particles then move towards t equal plus infinity. And in this final state, in general, I will have, so let me write it this way. I will have another collection of particles. My theory preserves energy and momentum in the scattering. So in the initial state, I have some total energy and some total momentum, and this needs to be conserved in the scattering. I will have the same total energy and the same total momentum in the final state. But of course, in relativistic theories, one thing that doesn't need to be conserved is the number of particles. You can have the same total energy in the final state, but realized with a different number of particles and different momentum in general. So I will call Q1, Q2, Qm. So this m in general is different from this n. And another thing that in general will happen is that in the theory I will have different species of particles. Okay? And I will use some labels to denote different species. So I will use the species label. This is A1, species A1, species A2, species AN here. And here let me use the notation B1, B2, Bm. So these species, for example, can be different charges carried by these particles. Now also charge will be conserved by the scattering, but it can, in general, redistribute among the particles in several ways. So this is pictorially the most general scattering event you can have. And the way it is characterized is to say that the probability that such an event occurs, you see, given an initial state, you can have many different final states, it's not unique. So you have some probability that a specific final state will occur, and this probability will be the modulus square of a scattering amplitude, what is called a scattering amplitude. That I will denote in this way. So Q1, Qm, S, P1, Pn. Let me also add the species indices in this way. So what's the meaning of this? Is that I have an initial state here on which I add with a scattering operator. So this is an operator which acting on the initial state determines the effect of the scattering. And then for the probability amplitude to have this final state, I will project the state I get from the action of S onto the final state I want to characterize. So this is the probability amplitude or scattering amplitude. For this process. As I said, the probability for the process is the modulus square of this amplitude. And the S matrix is nothing else than the collection of all these amplitudes. So this is an element of the S matrix, computed on this particular initial and final states. If I put in a matrix all the possible matrix elements with all possible initial and final states, I have what is called the S matrix. Now, the states I'm using here, so are the states, so for example here, are the states when the particles are at t equal minus infinity, for example. So I use this t minus infinity basis of states as a basis on which I compute the scattering amplitudes. So these states are called asymptotic states. And since we are at t equal minus infinity, the particles in these asymptotic states are very far apart from each other. And they are eigenstates of the energy of the quantum system with an eigenvalue which is just the sum of the energies of the individual particles. So here I'm introducing this H, which is the Hamiltonian of the quantum system in 1 + 1 dimension. So it's not, this is a quantum Hamiltonian, is a different object from the Hamiltonian Carly H that I had in the lattice model, okay? So this is the Hamiltonian for the quantum system in 1 + 1 dimensions. And similarly, in this 1 + 1 dimensional system, I have a momentum operator, which I call capital P, which acting on the state will give me the total momentum. So the state is the same. Okay, so we see that in general we have all kind of states that we are able to construct with these particles. There is a basic state, which you call the vacuum, and it is the state, just the state without particles. So this is a state which carries zero energy and zero momentum, because there is nothing inside. No excitations. So one thing that I just state now, and on which we will come back later, is that which makes the connection also with the phase transitions that we want to describe, is that when we have a spontaneous symmetry breaking in the theory, this will yield several vacua. Which are degenerate, they have the same energy, it's 0, and so they are interchanged by the symmetries, by the symmetry, G. So in such a way that there is a correspondence between the vacuum state you have in the theory and the phases you have, the possible phases you can have in the statistical model. So above Tc, the vacuum is unique because the symmetry is unbroken. Below Tc, you will have several degenerate vacua corresponding to the several degenerate phases, ground states of the statistical system. We will see this in practice later on. Okay. So the next thing we will do is to look at some general properties of these scattering amplitudes, because we will use this in an essential way at the moment in which we want to solve these field theories. And I will do this analyzing the simplest possible scattering event, which is the following. So let me draw it. So the simplest scattering event you can think of is the following. It's called elastic scattering of two particles. So the initial state you have two particles, P1 with the momenta P1 and P2, and species A and B. Now the scattering is called elastic if in the final state you have the same number of particles. So the number of particles doesn't change, it remains 2, and the same masses you started with. So I'm taking here same mass m for all particles. For the 4 particles I have here. So the final particles will have some species C and D, maybe characterized by some redistribution of charge, but the mass doesn't change. So I'm considering, as I said, the simplest situation, because also this will be enough for our purposes. Now, energy and momentum are conserved always in the scattering. Since we are in 2 dimensions, so given energy momentum of the initial state, we know the total energy momentum of the final state. But in 2 dimensions, so we have a single energy and momentum, a single component. So we have 2 conservation equations. And if all particles have the same mass, you can see immediately that these equations force the particles in the final state to have again the same momentum, P1 and P2. So in 2 dimensions, it works like this. So in the end, this elastic two-particle scattering is characterized by only 2 momenta and 2 energies associated to them. And this is why you see scattering amplitudes, since we are in a relativistic invariant theory, they will be relativistic invariant objects. And so they will be functions of relativistic invariant quantities that we build out of the energy and momenta involved in the scattering process. For this simplest case, since we have just these two momenta, there is a single scale invariant quantity that we can build. And I will write this in this way. I call it S, little s, and it corresponds to the sum of the energy squared minus the sum of total momentum squared. So this is the only independent relativistic invariant quantity you can write. And you see, if you go to the center of mass system, in which the total momentum is 0, this disappears. So you are left with the square of the total energy in the center of mass. So this is center of mass energy squared. So it has a very precise physical meaning. Now, the consequence of what I've just said is that I can give now a name to this. So I call this scattering amplitude S, A, B, C, D to keep track of the species for the particles. And there it can only be a function of this single invariant S. So I write it this way. Yeah.
How do you know that they only can exchange the momentum after the scattering?
I don't got the question.
After the scattering, how
Yeah.
do you know that they only can exchange momentum? I mean, they change the momentum, but the values keep the same.
Yeah, it's kept the same because, as I said, in 2 dimensions, we have 2 conservation equations, one for energy and one for momentum. Momentum has a single component. And these 2 equations, you have 2 unknowns. They determine completely the momenta of the particles in the final state. Once we have, in particular, once we have stipulated that the masses in the final state are always the same, this fixes the value of the momenta to be exactly the same. You can just write the conservation of energy momentum, and you see that you get this. So this is specific to the 2-dimensional case. If you go to higher dimensions, this will not be the case. Yeah. Yeah. No, I mean, if the particle have no mass, I put this m to 0 here, but still energy and momentum are constant. Of course, they will be related. They will become, so for 0 mass, the momentum will be just plus or minus the energy. Right movers or left movers. We are going to see that. It's just a particular case of what I'm saying.
But your argument was you have 2 equations constraining the dynamics of the system. But when it becomes massless, you only have 1 equation constraining the dynamics.
No, but I mean, look, going in the center of mass, this is 0. You just need to fix the total energy. And the total energy is fixed once you know P. That's it. Think for a moment about this. It's really trivial. Anyway, this massless case will be in the next lecture. So. Yeah, but he wants to take the mass to 0. But it's a particular case of the case with mass. Then, okay, so we can write this Otherwise, sorry, I don't see your point. What do you mean? That in the massless case you have no conservations? I don't get the question.
I think he was saying that the laws, so the two equations reduces to one because that's probably his point.
But you have to put the constraint. Some constraint becomes more trivial, but it is there. It is not. Think for a moment about this, and just write the equations, and you get the result. Now, what we want here is to characterize some main properties of this function. So these properties are somehow have been obtained from general studies of the scattering theory in relativistic theories. Here, I'm not going to do the history of this determination of these problems, of these properties. I will just state them. Explaining essentially what they mean. So, the first property is that the amplitude, so S, A, B, C, D of S, is an analytic function of S. Considered formally as a complex variable. So this is one of those cases in which you do a continuation of your variable to the complex plane in order to exploit some analyticity properties. So we go to the complex plane. So this will be analytic function of S up to some singularities that carry a physical meaning. So the first type of singularities are branch points which are related to opening of scattering channels. What I mean by that? In order to have a scattering, you need to have enough energy in order that that process is physical. So in this case, to have this process, you need to have at least the minimal energy corresponding to two particles, and the minimal energy corresponding to two particles is the sum of their mass. So the total mass will be 2m for two particles of the same mass. And the statement is that this so-called threshold value for the scattering process will correspond to a branch cut of a cut that we take this way. But then in general, since the number of particles is not conserved, with this initial state, with two particles, if you put enough energy to produce three particles, you will open, at that point, a new scattering channel. So this will be at 3m squared. So S is the square of the center of mass energy. So you will have here a new cut. And so on and so forth. You can, when you reach the threshold for production of 4 particles, you will have a new cut, and so on. So in the end, this becomes an infinite sequence of branch points and branch cuts. Now, the third point is that the other singularity you can have, they are poles, and these are related to bound states. So when these two particles scatter, they can form a bound state. with some mass, which I call m tilde. And this bound state, so it will appear as a pole below the threshold. The bound state, to be stable, needs to have energy smaller than the sum of the two constituents, so it will be below the threshold there. You can have one or more. For each one, you have a pole. Then fourth property is crossing symmetry. This is a property which is characteristic of relativistic scattering, and it says the following. I state it. We are looking at the scattering in this way. A, B, C, D. P1, P2, P1, P2. So for us, time is running this way, upwards. So when you look at the amplitude in this way, this is called the direct channel for the scattering. Now, what crossing symmetry says is that you can look at this amplitude in the so-called crossed channel, which is this way. When you look, so now your time somehow runs this way. And crossing symmetry says that the amplitude for the direct channel and that for the cross channel, they are related by analytic continuation in S, in the variable S. Now, the form of the analytic continuation, more precise, is like this. So this particle here, when you look in this channel, some particles will have the arrows, particle A and C have the arrows pointing in the right way, according to time evolution in this horizontal direction, and then you don't touch them. So P1, P1, A, C. But the other two particles, they have the arrow of time in the opposite direction. So what you do is you reverse the arrow of time, and at the same time you switch for particle to antiparticle. So from B to B bar, this bar means antiparticle. So particle with opposite charge with respect to B, but same mass, and this is D bar. At the same time, what you do in this operation reversing the arrow of time is to also to change the sign of both energy and momentum. So this will become minus T2 minus P2. And the same here, minus E2 minus P2. And now you compute the invariant here with this new configuration of energy and momentum. If you do this is another exercise you can do immediately. The statement of crossing symmetry is the following, that S, A, B, C, D of S is equal to S, D bar A, B bar C for M squared minus S. So this is the change in S induced by the fact that I'm reversing the sign of energy and momentum. You can start from this definition and perform the continuation. Then there is another point. So since I have these cuts in the game, if I want to work with the physical value of the energy, so real values of S, I also need to specify if I am on the upper or lower edge of the cut. This is why I add here an I epsilon and I take S real. So plus I epsilon means I have on the upper edge of the cut. And when I do here, since I have minus S in the continuation, I will get a minus I epsilon. So this relates with the lower edge of the cut. And you see a consequence, immediate consequence of crossing symmetry is that now, due to this relation, the original amplitude, which was this one, will get also the cuts, branch cuts of this second amplitude, reflected by this continuation. So this branch point here, it starts precisely like 4m square. If S is 4m square here, there will be a branch cut at argument 0. So this means that now I get, through this reflection, due to crossing symmetry, a branch cut, which is called the crossed branch cut, starting at the origin. But also the other cuts will be reflected. So I will get a new series of branch cuts, which are the crossed images of the original ones. So, and with this I move to the fifth property, which is unitarity. This is actually, okay, this is, as you see, the analytic structure is quite complicated in general. A main point for what we are going to do is that in the cases of our interest, this will simplify drastically. So this will be a main simplification that will allow us to perform our games. And so this is one key to exact solvability for the cases we are going to discuss. Then unitarity. Well, unitarity is a very fundamental property of the scattering amplitude. So the scattering operator is performing essentially time evolution. So it is a unitary operator. You have this. And in matrix element, this is something you can represent in this way, pictorially, as dagger. So if you have two, this is an operatorial identity. I can take it among some particular states. I take here among the two particle states. And here I can insert in the middle a complete set of my asymptotic states. In general, they will contain n particles. I will sum over all number of particles and all momenta. So this is a resolution of the identity. And this is a pictorial representation of this product taken on particular external states. Now, in order to produce an n-particle state here, you need to have enough energy to do it. So if the energy, suppose I stay in an energy range here, between the first and the second threshold. So in this region here, I can only have in the final state two particles. So this sum here stops to 2, n equal 2. Actually, it's the only one I can do, conserving energy momentum. So this simplifies in this range as 2m squared smaller than s smaller than 3m squared. This simplifies to something that I can draw like this. Because the only intermediate state here can be the two-particle one. And so let me put some indices A, B, C, D, E, F. I have to sum over E and F. And then, so this, for this case, this equation of unitarity can be written as follows: sum over E and F of S, A, B, C, D, S plus I epsilon times S, E, F, C, D, S plus I epsilon star. So this is transposed and conjugated, and then the identity taken between these particle states, two particle states, will be non-zero only if A is equal to C and delta is equal, and B is equal to D. So this is how the unitarity equation looks like in this range of energy, and this is actually the only thing we need for unitarity in the following. Yeah? What do you ask? Thank you, these are wrong, because I'm going from A, B to EF. And then I start again with EF, and I'm summing over EF. Thanks a lot. There is a last property that I just list, and it is called real analyticity. It just says the following, that if I take the amplitude, I can go from the upper edge of the cut to the lower edge by complex conjugation. And in particular, you can use this property here to get rid of your conjugation and change the sign here of the I epsilon. This is something we will use also. Okay, so these are a set of basic property of relativistic scattering amplitudes, elastic scattering amplitude, that provide us with all we need for the following. And in the following, we will see how all this simplifies drastically, and so the game will become really simple enough to allow solution. Okay, so yeah, yeah, yeah. As I was mentioning, so these have been originally deduced from massive studies of perturbation theory, for example, for scattering amplitudes, in which you study all these properties to all orders as far as you can, and then finally they have been axiomatized. So there are, if you take the basic text for this piece of theory, which is called the Analytic S Matrix, the book by Eden, Landshoff, Olive, and Polkingorn, they are given as axioms.
Yes, but what I wanted to mention is that you should recall that real analyticity is related to causality, that unitarity is related to probability conservation. I mean,
Okay. Well, yeah. Yeah, there is, as Filippo is saying, you see unitarity here expresses the fact that the probability in the scattering is conserved. If you think to what these matrix elements mean, if you think of S as matrices, you will see. So this equation means that the sum of the modulo square of a row of the matrix, which is the sum of the probability for all possible final states given an initial state, has to be 1. So it expresses the fact that the sum of all possible probabilities is 1. And again, real analyticity is related to the fact that I can going from the upper edge of the cut to the lower edge is somehow related to exchanging the sign of time, and in this sense it is related to causality. So there are a number of further remarks you can do if you are interested in going deep into the origin and the specific derivation of these properties. I suggest the book I just mentioned, which is the reference for this subject. But I insist on the fact that the game will become simpler in the following, and what we have just said now will be more than enough for what we need. Sorry, I wanted to conclude just listing do I have 5 more minutes or? Okay, I will stop it here. I will start with this tomorrow, since we are already 5 minutes past the schedule. Thank you. I mean, this is general. Any ambiguity of phases is built in.
Yes matrix.
Yeah.
Matrix is the matrix element between two states.
Right.
Different states.
Yeah.
The phase, the states are defined up to a phase, meaning I can choose arbitrary with the phase of the states.
Yeah.
Then I can choose for these states phases which aren't analytic functions of S. Then clearly the first point, for example, wouldn't be true.
No, I mean you don't have such a degree of choosing phases.
Quantum mechanics, I do have this freedom.
The matrix is defined in terms of specific states.
Yeah.
Which states? So states are the
These are the asymptotic states, I said at the beginning.
I mean, quantum mechanics, you can, if you have a state, you can also have e to the I alpha for the same state, and this is just as well the same state. It gives all the same predictions. Now here the problem is that the S matrix is given, I mean, for the diagonal terms, it's okay, because this arbitrary phase cancel out. But for the non-diagonal terms, this phase, I mean, of course, that would be you would have to choose a logical phase.
I mean, you start with a given you start with a given basis, and
Yeah, but they have the same matrix. So no matter what function of S it is.
so well. These properties are general once you have fixed your initial basis of states, and this is the general theory and general properties of this matrix. There is no such an ambiguity. this, I mean, this is really very general theory of scattering.
You have a prescription on how you get phases to states. Yeah, but you can always choose phases. I mean, if the S matrix wouldn't be an analytic function of S, you can choose phases such that it's always an analytic function of S. So, I mean, since you have this auxiliary, you can, I mean, for example, take a phase e to the I1 over S, this is non-analytic, then you put this phase in front of a vector and you get a non-analytic S matrix. But,
No, look, I mean, there is no such freedom in the game. If you start from the very beginning, as I said, in the end, these are given as axioms. But if you start from the derivation of this axiom from perturbation theory, so you have a well-defined starting point, and so these properties follow from that starting point without ambiguities. So it's not maybe so obvious to see it from here, but this is a very constrained game, and these properties I gave here are general. Yes.
Can you say once more how you arrive at 4m squared minus s in the crossing symmetry?
The crossing symmetry here?
Yes. How you arrive at 4m squared minus s?
This comes, if you take the definition of S, so S was the sum of energies square minus sum of momenta square. So this is S in the direct channel. Now, to do the connection, you want to compute now the argument here of the scattering in the cross channel. Did I erase it? Yes, I erased it, sorry. But in the cross channel, you have to switch here from E2 and P2 to minus E2 and minus P2. And this, if you do this exercise here, is going to change. Remember, you have to use also the condition that for each particle, E square plus equal P square plus M square. If you use this, you will find this new argument for the crossed amplitude. It's a very direct computation. Yeah.
Might be simple, but
Yeah.
at the beginning, you defined the order parameter should be the expectation value of a spin variable.
Yeah.
But, I mean, the order parameter depends on the model, right?
Yeah.
In general, how can I extract the order parameter from the symmetries of the model? Or
Well, you see, for the models I've introduced, for the easy model, the order parameter was the spin variable Si. This is the property that given the symmetry in the disordered phase, so this takes values plus or minus 1. In the disordered phase, you get 0 for the average. For the Potts model, I started with the side variables Si going from 1 to Q, but then I said the proper order parameter according to my definition is sigma I alpha equal delta Si alpha minus 1 over Q. So I did this definition precisely because with this definition, this becomes the order parameter according. What is the goal? The rule. Well, there is no. For each model, you look for the appropriate spin order variable which has the property which vanishes above TC. But this is the definition. I mean, there is no deep physics inside this. I don't see what you mean.
I mean, because you have to perform calculations in order to show that the order parameter vanishes after t equals to TC. Some t equal to TC,
Now, in what I say, the vanishing of the order parameter suitably defined just comes from the fact that above TC the symmetry is unbroken. So is a consequence of the fact that the symmetry is not broken that allows you to say what the value, the average value of the spin variable will be in that phase, and then out of that you can construct a variable sigma which enjoys the properties of vanishing above TC.
So if I give you any statistical models, are you able to give me the order parameter of it?
What do you mean any statistical model?
I can use graphics model.
Oh my God! No, I don't want to go into that. No, I'm not. As I said, what I'm doing here relies on very simple ideas of symmetries. But for each model, it's true that you can find the order parameter. It can be more complicated. I introduced just basic models, but it's not.
But there is no rule for that.
There is no.
Rule. A prescription.
Within my framework of spontaneous symmetry breaking, this is quite straightforward. I'm not pretending to that any model you can have will fit immediately into the scheme. For example, here I'm taking a ferromagnetic interaction, which is not always the case. So, but I'm doing this because I'm interested in describing universality, and considering the ferromagnetic interaction is the simplest way to discuss this feature. In the end, if I have time, I will do also some example with antiferromagnets to show how in the antiferromagnetic case you still can do similar field theoretical descriptions. But there, of course, there are other features that need to be discussed separately. So please consider this point.
Let us give private question.
Yeah.